I've been asked to make a video explaining why it's okay to ignore the effects of gravity in the case of the simple harmonic oscillator. So in this case, what I've done is drawn a picture of the simple harmonic oscillator, and we've included the effect of gravity. And we recognize that due to the weight of the mass, the equilibrium position is going to be a distance x0 from where we initially started. In other words, without gravity, we'd expect the mass to rest here, and because of the added weight due to gravity, the spring deflects by an amount x0. We also know that x0 is such that k times x0 is equal to the weight, which is mg. So what I've done is I've drawn two coordinate systems. On the left we have coordinate system x, and on the right it's y, and these differ by the initial displacement, the displacement due to the mass, the weight I should say, x0. So I can write that x is equal to x0 plus y. Okay, so if I draw the free body diagram of this mass, let me do it over here. Oh, not a very good one. And this is the mass. Of course, in the downward direction, we've got the weight, which is mg, and opposing that, we've got the spring force, which in this case is k times x. And based on what I've written, we can also write that as k times x0 plus y. In other words, the spring force is equal to the spring force due to the weight, which is k times x0, and then we displace it beyond that an additional distance y, and as a result we get a spring force k times y out of that. Okay, I could redraw it like this, maybe make it a little bit clearer, where we say that this force here is k times x0. Oops. K times x0, and we got a force here that's k times y. Okay, and then of course downward we have the weight m times g. So I'm going to go back to this first diagram and apply Newton's second law to that. And remember, this is based on the x coordinate system, so we're going to say that m x double dot is equal to mg minus kx, which is equal to mg minus kx0 minus ky. Let me give these some numbers. Call that number 1 at the top, call this one number 2, we'll call this number 3. Okay, and the point is we can simplify this because mg minus kx0, those cancel, those are exactly the same, based on equation 1. Okay, and then the other thing to realize is if I take the derivative of equation 2, let me do it in black, since x is equal to x0 plus y, if I take the time derivative, therefore x dot is equal to just y dot, because x0 is a constant, right? And same thing with the double dots, obviously. X double dot is equal to y double dot. So I can rewrite equation 3 as y double dot minus k times y is equal to 0 now. We'll call that equation 4. I left out my m, excuse me. So my double dot minus ky is equal to 4. And of course, this is just the original simple harmonic oscillator. We know the solution to this. This is simply y of t is equal to c1 cosine omega sub nt plus c2 sine omega sub nt, where omega sub n is equal to the square root of k over m. Don't know why I put brackets around that. Actually don't need those. We'll call this equation 5. We'll call this equation 6. So what have I done? I've basically said if I replace this original coordinate system of x by another coordinate system y, where instead of what I've done is I've zeroed it out. So effectively what I've done is I've said instead of looking at the oscillations about the 0 point, let's look at the oscillations about the x0 point. And then everything else is the same. And the x0 point, this point here, is known as the static equilibrium position. Okay. So that's why, and by the way, I should mention that, of course, in this sense, y is just a dummy variable. I could easily replace that with an x, right? But the important thing to notice is that y is about the equilibrium position rather than the initial 0 position. So if we call the 0 position this position here, then everything remains the same. Okay? And then fundamentally, we know what the solution to this looks like. It looks something like this, depending on the initial conditions. And this point is now 0, and this axis is y. But I could just as easily make this axis x and make this the x sub 0 point. Okay? So that's why when I say in problems involving the simple harmonic oscillator, you can ignore gravity as far as the translational mass is concerned. This is what we're meaning, that the assumption is that we're actually finding the equations of motion around the equilibrium point, and when that happens, the force of gravity, or the weight due to gravity, is exactly cancelled out by... Now, if we switch quickly to the pendulum problem, why is that different? Let me do it down here. Whoops. So if I've got a pendulum, this is some angle theta, and we've got mg here. This is m. The restoring moment due to gravity in the pendulum, which I'll say is m0, that being the 0 point, is something like minus mg, the weight, times this moment arm. And of course, for small thetas, we can just say sine theta is approximately equal to theta. But because of this, in the case of the pendulum, the force due to gravity, or the restoring moment, is actually a function of your variable, of your coordinate, or the degree of freedom. And the other thing, of course, is that as theta goes to the other way, it's always opposing theta, which is why it's a restoring force in this case. Okay, so for pendulum problems, you always have to include gravity. And for these simple harmonic oscillators or translational problems, it's okay to ignore gravity on the assumption that you're starting about the equilibrium position rather than the 0 position. All right, so let's just say you don't believe any of this, or you don't like this explanation, and actually we believe that gravity should be included and we should treat this as an external force. Well, we can try that method too and see what happens. Let me turn the page. Okay, so there we go. I've copied our problem again. Gravity is present in this case. And what we're going to do now is treat the gravitational force as an external load. Okay, I remind you from your calculus from differential equations. Let me just write the equation, and then we'll talk about the solution. Let's do it in black. So, ignoring what I said in the previous slide, we're starting now at the 0 point, not the x0 point. We haven't let this thing deflect due to the weight. What the equation would look like is mx double dot plus kx is equal to, and instead of 0, now we have mg. What was my last equation? Was 6, so this is 7. Equation 7. Okay. Now, I remind you that to find x, it's x of t, it's the sum of the homogeneous solution plus the sum of the particular solution. So let me write that. It's x homogeneous of t plus x particular of t. And just as a refresher, the homogeneous solution is found by setting this side equal to 0. And we've done that over and over again. The particular solution is found using something called the method of undetermined coefficients. And before I even get onto that, let me mention that in the case of mathematics, we call these the homogeneous and particular solution. But in the context of mechanical vibrations, this is the free vibration problem, or the solution to the free vibration problem, and it's actually known as the transient solution. Usually because if there's damping involved, these vibrations will actually die out eventually. Transient solution. Okay? Whereas the particular solution to the problem is known as the steady state solution. So sometimes in some problems they'll ask you to find the steady state solution. What they're actually asking is find the response once the transients have died out. Just find the particular solution. All right, so let me remind you that we use the method of undetermined coefficients. And we're going to treat this now as a forced vibration problem. Undetermined coefficients. And I'll remind you that if the right-hand side is a polynomial, then we assume a solution in the form that x particular of t would be equal to, I'll use the constants d. It would be d0 plus d1t plus d2t squared plus dot, 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 all the way up to whatever the highest power of t is on the right-hand side. Okay? Even if this side were t squared, we would still include all the terms of order less than t squared, all the way up to t squared. Now, in this case, mg is just constant, so we can say it's t to the 0th power. So in fact, all we need is the d0 term. All right, we call this equation 8 and equation 9. And the idea now is to put equation 9 into equation 7, and then we compare the coefficients of the powers of t. In this case, there is only one power of t, and that's t to the 0. So what does that mean mathematically? We want to substitute 9 into 7. And when we do that, we end up with, well, the second derivative cancels out. So we end up with k times x, which is just k times d0, is equal to mg. And this is very simple, that d sub 0 is mg over k, which is the particular solution, right? So x particular of t is equal to mg over k. We'll call that 10. Let me continue on the same page. I'll remind you that the homogeneous, or the transient solution, is equal to C1 cosine omega nt plus C2 times sine omega nt. Call that 11. So therefore, the full solution, x of t, is equal to C1 cosine omega nt plus C2 sine omega nt plus mg over k, and that's equation 12. All right, now we've got to apply our initial conditions, and in this case we'll assume that both the displacement and the velocity initially are 0. So the initial conditions are that at time equals 0, x of 0 is equal to 0, and also x dot of 0 is equal to 0. We'll call these we'll call these 13 and 14. Let me write it up here, 13 and 14. Okay, so applying the initial conditions, which means we'll put 13 into 12. 13 substituted into 12, or 12 into 13 actually it is, but fine. X of 0 is equal to cosine of 0 is 0, so that just gives us a C1. Sine of 0, cosine of 0 is 1, that gives us a C1. Sine of 0 is 0, so the C2 cancels out, plus mg over k equals 0. This implies that C1 is equal to negative mg over k. We'll call that 15. Okay, now we want to put 14 into 12, or 12 into 14. I'll write it again, 14 into 12. X dot of 0 is equal to, well, the first term gives me an omega n times C1 sine of omega t, and at 0, that's 0. So let me just put in a 0 there. The second term will give me plus C2 omega sub n times cosine of 0, which is 1. And then the last term is going to give me 0, because the derivative of a constant is 0. And this is equal to 0, and this means that C2 is equal to 0. All right, so in fact, the final form of the solution, x of t, is equal to x1, which is minus mg over k, times cosine omega nt plus mg over k, which can be rewritten as mg over k times 1 minus cosine omega nt. We'll call this equation 16. All right, so here what we have is 1 minus cosine omega nt. So this what's in the parentheses, if cosine omega nt is 1, this is 0, which is what it is initially. And if cosine omega nt is minus 1, then this is 2. 1 minus minus 1 is 2. All right. And this is going to oscillate between 0 and mgk over 2, or 2 mgk over 2. So let me try to draw that on a chart. 0, 2 mg over k is up here, and here is mg over k. And I'll remind you from before that we said that mg over k was just something we defined as x0, where x0 is simply the static deflection due to the gravitational effect, which is to say the weight. So what I'm going to do here is just neaten this up a little by writing it in terms of x0. So this would be, whoops, wrong color. This would be x sub 0, and this would be 2x sub 0. And let me just use a ruler for this. And what we have here is fundamentally a cosine curve that looks something like, let me see if I can draw it. All right, good enough. So what's happened is I've got a sine curve that's effectively about this point here, which is x0. I can redraw that. Let me do it down here. If I were to say, well, let's have the equilibrium position as x0, like we did previously, then it would look something like this. Okay. So what I've effectively done here is exactly in the previous problem said, you know, if we can assume that we're solving this problem about the static equilibrium position, let me write that here, equilibrium position, then this just becomes the simple harmonic oscillator all over again without the effect of gravity. So in summary, again, what gravity does is it just shifts this point by an amount x0. And once you do that, on the assumption that you're doing it about the static equilibrium point, you can now ignore the effects of gravity. Anyway, I hope that explains it, and I hope you found something useful in this video. Please feel free to leave us comments below or give us a thumbs up if you found something useful, or better still, why don't you subscribe to the channel? Thank you very much for watching, and we'll catch up with you in the next video.